Assalamu alaikum. Good morning, students. So today we are going to learn about the Navier-Stokes equation. Okay, so these equations I will try to derive it, and I will explain the details of the derivation, and I will also try to find out or highlight that how these Navier-Stokes equations we can derive from the Euler equation and how these two equations are different. Okay, so before going to that, we need to know the three things, that is gradient, divergence and curl. Okay, so we have three videos. So this video I will show it when we meet on WebEx. So from there you will understand the physical meaning of these three terms, that gradient, divergent and curl. Okay, so but how we can represent these things, this gradient, divergence and curl. Okay, so here is the mathematical expression. So gradient, we call this grad f. This is, remember, as a vector field. We use these things, the gradient, divergence and curl, in the mathematics to describe the physical meaning of any particular object. So to understand the physical meaning, you have to watch the videos. Okay, so here I just explain the mathematical representation. So gradient f, we call this nebula f. Okay, we call this nebula. So nebula is an operator, we call it nebula, and nebula we call it like this, del by del x I plus del by del y j and plus del by del z k. So this is for three-dimensional case. You can also consider del x and del y in case of two-dimensional case. So if you consider grad f, so if you put f here, you just need to put f. Okay, so it means you are differentiating a particular function with respect to x, y and z direction, and for each component we have one particular direction, that is I, j and k, that represents the unit vector along x, y and z. I hope you understand. So remember that grad f means what? Del f by del xi, del f by del yj and del f by del zk. Okay, so this is the mathematical representation, nebula f, nebula k. So you can write not necessarily f, you can write any function, and the function should be given. So could be like f could be x square plus 3y plus maybe 7z square. So what you need to do, so here del f by del x, you have to differentiate this function with respect to x. In this case, you have to differentiate f with respect to y, and again you need to represent f with respect to z. Then you will get the expressions. That expression will represent the gradient of that function. Okay. So next is divergence. So divergence, we call this diff f. Okay. This is a scalar field. Remember. So divergence is always a scalar. So we use the nebula dot f. Nebula dot f. So in this case, nebula, you already know that del by del x, del by del y, del by del z. So we just consider the component, okay, because we are considering the dot product. Similar way, for f, we have the x, y and z component. So if you know that a dot b is what, so if you consider this dot product, this is basic thing. So it should be del fx by del x plus del fy by del y plus del fz by del z. It means we are differentiating the x component with respect to x, we are differentiating y component of that function with respect to y, and we are differentiating z component of that function or force, whatever it is, with respect to z. Okay, so in this case we are differentiating same function with respect to x, y, z. In this case we are considering the component, x component with x differentiated with x with respect to x, y component which is differentiated with respect to y, and z component is differentiated with respect to z. Okay, that's how these two are different, and gradient is always vector, and we have the divergence is scalar field. Okay, Laplace equation, you all know this one. Laplace equation is nebula square f. So Laplace is actually we call this delta f. Okay, so this delta is actually is the second order nebula. Okay, so you can represent in this way, you can represent in this way, or you can represent in this way, similar way. So that is you need to consider the double derivative. So double derivative of function del square f by del x square, del square f by del y square, del square f by del z square. So here you can see that what is the difference between the grad and Laplace. So we are considering the differentiating two times, right? X, Y, Z, and this is also a scalar. There is no vector field. is that it's just satisfying the Laplacian equation. So we call this Laplace square. So this is the thing. Okay, so I hope you understand the gradient, divergent, and this is the Laplacian form. So you have to remember which one is the vector, which one is the scalar field, and how we can calculate. And the next thing is curl. Curl is the cross vector. So it is actually nebula multiplied by this f. Okay, nebula multiplied by f is a cross product, not dot product. So in this case, we can represent, if you have this one, you have I, j, k. You know that how to make the cross product. So this is nebula is del I, del x, del by del y, del z. We have x, y, z. So then you multiply it. So you know how to do the multiplication. I, then you just multiply this minus this plus j, and then you have to consider this multiplied minus this, and k, how you consider it. So we consider the cross product. Okay, so this is also a vector. Remember, curl is a vector. It represents the rotation of any particular object. Okay, it represents the rotation of any particular object. So I just try to highlight few things. Gradients. Gradient we use to find out the slope. Okay, slope at any particular field. For an example, the golf club. So for an example, in the golf club, or we can say for skiing. Okay, not in the golf is also, yeah, possible. We need to measure the slope. Okay, how much force we need to apply to make the ball to enter to the particular hole. In case of skiing, we also need to find out, we need to control the speed. Okay, based on the slope, so that we have the full control when skiing on the surface, skiing on the maybe on the ice, is the same thing. So we need to actually calculate the gradient. Okay, gradient means the slope, the steepness. So to get in the more detail, we will learn from the video. But for now being, I can say that if I want to highlight about this grad, okay, so grad f is actually is actually rise divided by run. What is rise and run? For an example, we have the contour map. Okay, so we have the contour map, means this contour, this line represents the height, the water level height or the field height, maybe 90 meter. Okay, this contour is actually representing the height, the level of height, 100 meter from the sea surface. Okay, from one particular baseline, for an example. So then if you want to find out what is the gradient for these two contour. Okay, for an example, here we have the A. Okay, and we are moving towards, sorry, this direction, that is B. So, and this is eta, this is the vector, unit vector of the gradient, A to B. Okay, so for an example, so in this case the grad f will be, you have the rise. So how much rise you have in this case? So you have, from the contour map you can find it 90 and 100. So the rise is actually 10. Okay, the rise is actually 10. And now let's try to find out. Okay, you want to go from A to this point. You want to go from A to B, C point. Okay, so now using the scale you try to find out what is the value. It means how much is the distance from A to C. For an example, on the horizontal line, if you consider the top view using the contour map, you find this AC, the distance of the AC is, the horizontal distance is 30. Okay, so the run is actually 30. So in this case your gradient will be 10 divided by 30. So this is the way we can calculate. So for an example, you want to find out the slope. Okay, so if you want to find out the slope, what is the slope of AC line? The slope of the AC line will be, for an example, if this unit vector along the AC is u. Okay, so in this case it should be the vector along this u, and then you just need to multiply the grad f. So this one, sorry, you will see in the video, okay, how it's interlinked with each other. So mainly we use this one to consider the slope. Okay, slope of any particular, maybe as I said, during the skiing, or if you want to consider the golf club, whenever you need to measure the slope of any particular given line, if you know the grad, okay, if you know the rise by run, so then you can just multiply it with this the vector along that line. Okay, so these are the physical application. In case of divergence, okay, in case of divergence, we normally consider this one for establishing the relationship between the multiple factor. For an example, in the uranium field, or maybe in the nuclear field, where we have the uranium gas, okay, uranium metal, and we have the fusion is occurring, and you need to establish the relationship between the maybe the temperature theta. For an example, then you need to establish the relationship between the rate of change of heat exchange, how much, maybe that could be like, for an example, J, the rate of flow heat energy, and we also have the source of heat, right? The heat generation, heat is generated in the nuclear field, so maybe it's S. So if you have the, so you know the theta, theta of the rod, maybe in the rod is that rod where we will pass the uranium gas, okay. So what is the temperature distribution? So this temperature depends on the heat rate of heat flow or heat exchange rate, and also the source generation. So in order to establish these kinds of relationship, we use the divergence, okay. So this one I will not explain here. Maybe you will see the video, then you will learn. And the curl, is we use it to define the rotation. Okay, so rotation of one particular object. For an example, we have the river bank here, and we consider the flow is uniform, or flow in this direction. Okay, so normally we will find that if you put some any object here, you will see that this object will rotate here this way, and if you put any object on the right hand side, you will see it will rotate in this way. At the center line there will be no rotation. Okay, so it means that you will have this rotation in the left hand side, you will have the rotation on the right hand side. At the middle you will not have any rotation. So in order to define these kinds of rotation, we use the curl field. Okay, we say that we have the curl here, we have the vortices. Okay, we also use the curl field to explain the hurricanes or tornadoes. Okay, whenever there is a rotation, we use the curl. Anyway, these are just a brief explanation, but when you will see the video, you will understand. But mathematically, we will derive, we can use these expressions in this way. Okay, so we have a few more things. So if the flow is incompressible, okay, if the flow is incompressible, it means like you cannot compress the flow. Incompressible fluid means the density will be always constant. Remember that in case of incompressible flow, the density rho is constant. So we call this so we call that the divergence of the velocity field is actually zero. There is no change in the force in x direction, y direction, and z direction. So what does it mean? In this case, this is the divergence of v velocity field is zero. It means that del vx by del x, okay, plus we have the del vy by del y, plus we have the del vz by del z is actually zero. It means the change, if you consider the change, total change in the velocity field, there will be no change in the velocity field, because it's an incompressible fluid and we cannot compress. If you cannot compress, so the total change, even you have the change, if you consider the measurement of the change, if you sum up, so resultant change is always zero. So that is the boundary condition, or we can call this equation will be always satisfied. Then equation of continuity, you also know that equation of continuity will be also satisfied in case of incompressible fluid. It means if the flow is continuous, there is no discontinuity. Okay, that means that if you differentiate the velocity in x direction with respect to x, sorry, del v by del y and del z, del w by del z, this is the equation of continuity. This is also zero. And in case of cylindrical coordinates, so this equation can be represented in this way. I hope you already know these things. So this is the equation of continuity in polar form or cylindrical form. Okay, so 1 by r del r by u r del r, 1 by r del u theta by del theta, and del uz by the del z, sorry. So in case of cylindrical coordinate, we have u, r, u, theta, and z, these three coordinates. So in this case, we have x, y, and z. Okay, so we have the z is common, but instead of x, y, we have the radial direction and we have the angular direction. Okay, so we have these three coordinates. So anyway, so this is just a practice. It means just recall the memory, so that you have already learned in your fluid 1 course. Okay, so let's try to find out how we can derive the equation of the Navier-Stokes equation. So I will go one by one. Okay, so later on you will see how I develop. Okay, so I will not explain just from the last to the end. So we just start from the beginning and we will develop the flow. Okay, so to derive the Navier-Stokes equation. Okay, so in this case, let's consider a fluid volume. Okay, let's consider a control volume. Control volume is the volume that represent the fluid here and is moving along the fluid. So we just consider the maybe you can say that the volume of interest or the control volume. So if you consider a three-dimensional cube, okay, as a control volume, so what are the forces acting on the control volume? So if you want to find out the force, you have to measure that what kind of force we can have. So one is the summation of the force inside the body, and another one is the force that is acting on the surface. So we have two different things. Okay, one is inside the body and another one is surface. And when we consider the surface, we have surface in and surface out. Okay, and we call it we are not considering the complex flow, we are considering the flow is in one directional. Okay, so we try to derive the flow for one directional, for an example for along the x direction, and similar way we can write that the equation can be written as for y direction and z direction. Okay, so the force act on the control volume, total force is acting on the control volume is the change in the momentum change. Okay, so you know that the force is actually is equal to change in momentum, is proportional to the change in momentum. It is change in the multiplication of mass and velocity. This is Newton's third laws of motion. Okay, so it means the rate of change of momentum should be equal to or proportional to the applied force. So that is the rate of change of momentum. Okay, so it said that is equal to the momentum change in the control volume. It means that within the control volume, that is the body part, plus the rate of which the momentum flow out of the control volume minus the rate of which the momentum flow into the control volume. It means the mass flow out minus mass flow in, that is the resultant input. Okay, so we can write that m is equal to rho v. So you can see that inside the mass we need to consider the volume. Inside the body, if you consider the total body force, so we have the m is equal to rho v. Okay, so we have rho v, then we integrate for the volume, for the control volume. Cv means control volume, and because we have the rate of change, you need to consider the dot. Okay, so it means that you need to derivative by del t. It means the change of rho v, it means m dot. So m dot means rho v dot. So in this case we call it del t of rho v. Okay, so this is the part for the body part. On the other hand, we have the out minus in. So how much is the out is mass flow rate. Maybe the m dot is the mass flow rate out multiplied by v, and then minus m dot, and this one v is same is in. If the both are same, actually that will be cancelled out. Okay, but if we have different values, we have the net mass in. So in short, the total force acting on the fluid volume will be the body force plus the surface force, and in case of surface force we have the out minus in. And you know that why we call this mv, because F is proportional to m dot v, that is the Newton's third laws of motion. It means rate of change of momentum should be proportional to the applied force. So we just consider the same Newton's third laws of motion. Okay, so now we need to split the things one by one to go into more details. Okay, So now let's consider the body part. How much is the body force we have? So we say that we have sorry, becoming slow. So last time we said that we have del by del t is rho v, but actually how much is the force is acting? Okay, so we know that F is equal to ma. We also know that from the Newton's second law. Okay, so and we have that m is equal to rho v, and we have the acceleration. So normally when we have the body here, we consider that only we have the gravity force acting. Okay, we don't have other force acting on the body, and the gravity force has gx, gy, zz, but we know that we only have the x directional gravitational force. We are not considering the gy and gz in this case because we are just considering the x directional motion. But normally we know that the gravitational force only acts in the z direction, but later on actually we will see that there is actually no gx and gy exist. But anyway, for simplicity we consider that it has three components, gx, gy and gz. So the body force in x direction will be, due to the gravity, will be rho is a rho. Acceleration we call is that the acceleration due to the gravity we call is replicate this a by gx, and in case of v we consider the dx dy dz. This is the volume, right, for the control volume. So that is your body part. Okay, so now we need to find out the total surface. Okay, in order to find out the total surface, you need to consider all the surface forces acting on the cube, on the control volume. Okay, so how we are going to do that? So this is very simple. Okay, I hope you already know these things. So before going to that, you need to consider which one is x, which one is y, which one is z. So here you can see the x direction is this one is x direction. Okay, this is x, and y is, in this case they consider vertically y. Actually you can consider as you like, but I just stick with this one. So this is y, and this one is z direction. Okay, anyway, that's okay. So what we need to find out, we need to consider the x directional force. Of course we have x, y and z, so we just focus on the x directional force now. So here we have the surface. Okay, so we need to consider the normal force and also the shear force. We need to consider two things. Okay, one is normal to the surface, and another one should be shear, that is tangential to the surface. So let's consider this surface here. Okay, so this surface, normal to the surface force is this one, is along the x direction, right? So we have sigma xx. Sigma xx means is a normal force. We don't have any coupling term, so that is normal force. Okay, so how we can calculate the force? So we know that stress is equal to force by area. So force will be stress multiplied by area. So here we are considering force. So this stress should be multiplied by area. Which area? The area, the cross-sectional area at which it is working. So what is the cross-sectional area here in this case? So this is the area, right? So this one is dz, and vertical is dy. So that's why we multiply dy and dz. So this one is done. Then we have because the sigma x is actually acting at the center, okay, at the center of the cube, but now you are focusing on the surface that is at a distance of dx by 2. Okay, if this is 0, if this is a center, so the distance here, the total distance is dx, so half of the dx will be from here to here. That distance is dx by 2. So we use the Taylor series, Taylor expansion. So sigma x, I hope you already know this thing from fluid 1. So sigma x plus, you have some increment due to this surface difference, so that should be del sigma x by del x and dx. Okay, it means that sigma xx plus del sigma xx by del x multiplied by delta x. So delta x in this case, the distance of the surface from the center, that is the dx by 2. Okay, so if you have this one, understand. So how about the opposite one? Opposite is same, you just copy it and then just make it minus, because in this case it's going opposite direction. It's not along the x direction, it's going opposite to the x direction, positive x direction. So we should have minus. Other things should be same. Okay, so that is the normal part. Normal force is there. Now we need to consider the tangential force. So which one you need to consider, which one you want to focus on? You want to focus here. It means the surface force acting on this surface. Okay, so in this case you need to focus on, you are considering here and here, up and down. Okay, up and down. So the vertical distance between up and down is which one? dy. Okay, so we have y, actually y. So remember this y. So when you write this expression, you need to write the contribution is actually for y along the x direction. So we need to write sigma yx. Okay, so first of all, when you write the notation, the first alphabet will be the contributing part from which direction. So this one we are considering y directional contribution in x direction. So we are considering the component of y in x direction, shear stress. So this one is sigma yx, then del sigma yx by del y, because it's y directional. So as I said, it's up and down. So you have to consider up and down the vertical distance. The separation is along y direction. Okay, you can see here also from where is my, you can see this vertical is y, and then del y. So this one dy by 2 is same like this. Now you need to focus on the cross sectional area. So the area is which one? This one, right? So in this case, along this direction is x, along this direction is z. You can see along this direction is x, along this direction is z. So this is the part is ds dz. So if you write this one, you understand this one, just write the opposite one, same, just you write minus. Next, you have the left and right. Next, you will have this one and this one. Okay, so this surface. I'm sorry, this one vertical is already done. So this one is actually sigma xx, right? This one is sigma xx. So left right is done, up and down is done. So now is fore and aft. So you have this fore is a backward and forward. Okay, this part and the backside part. So where is the contributing part? This one. So up and down, it means you can see that fore and aft, this direction. Okay, so this is z actually. You can see this is z. So in this case, we have the sigma zx, and then sigma zx by sigma z. Sigma del sigma zx by del z. I'm sorry, and then dz by 2 is like this. Now you have to find out the cross sectional area. Cross sectional area is which one? Your cross sectional area is this one. It should be dx dy, right? Dx dy. So this should be dx dy. You need to give some time, and then you will understand. So once you're done with this one, you can also write the same thing for the forward part here. It should be just minus. So now how many components you have? You have 6 components of stress. So out of 6, 2 are actually normal stress and 4 are actually shear stress. Now you need to find out the surface. Okay, so the summation of the surface should be out minus in. Okay, so in this case, how much is the out, how much is the in, you need to find out. So by considering the net force acting on the differential fluid in the x direction, so your flow, the surface is actually approximately this much. So you can see here, we just consider sigma x, sigma yx, sigma zx. Why we are not focusing on the minus part? Because we consider the flow is we call this, there is no loss of flow. It means this opposite direction we don't have any flow. Okay, we are considering the flow in this direction, and we only consider along the positive x. Okay, so we are considering only positive x directional force. So we just focus on the positive x directional component 1, 2, 3. And once you try to put it together, you can see that sigma xx, okay, and we have del x and del z, and this part will be cancelled out. Okay, so in short, we will have this one, del by del x. In this case, we have the sigma x, and we have the del by del y, sigma yx, and we have the del by del z, sigma zx. So if you try to write it down from the beginning, we will have this minus this, so this should be, you can replicate the things. Okay, I write for you one time. So sigma xx, so this is the in, sorry, out. Okay, so out sigma xx, so that should be dx by 2. Okay, dy dz. Then we have the minus, so outflow in the opposite direction flow, that should be minus sigma xx dy dz. Okay, and then we have minus minus plus, we have del sigma xx, that is just you need to balance the force, and we have the dx by 2, we have dy dz. So you can see this will be cancelled out. Okay, so in this case I missed out this one, dy dz we should have here, so this one will be cancelled out. So we have del x dx. Okay, del x, and then we have this dx by 2, it will become only dx, and we have dy dz. So we have this term common. Okay, it means that when we consider this minus this, this minus this, and this minus this, so positive minus negative, we consider the x directional flow. So net flow, you will get the things like here. Okay, so as I said that normally even you don't calculate, so we are considering this much, so that will be cancelled out. Okay, and we will have these two components that will add it up. So simplified, so just you can write it all together in this way. Okay, so your net force is actually surface force. In this case we have this much. Okay, so this one is normal force, this one should be the shear. One minute. Okay, so next is we need to continue our derivation. So we have already all the components ready. So now we have the acceleration part. So we know that the Newton's second laws of motion is F is equal to ma. So m and a is acceleration dv by dt. You can use a small d, should be also okay. M is equal to rho v. Okay, so now you have this equation ready. Then what you need to do, so just put the values there, total force. So this is ma. Okay, and then we have this gravitational force, that means the body force in this case due to the gravity, and this much is the surface. Okay, so we already calculated this one. This is body and this one is surface. Surface we got it from surface out minus surface in. So this equation can be simplified as rho dv by dt. This one we can actually make it a vector field. It's simplified means it's for a three-dimensional case. So we can write rho and v should be here. So this gx, this part we can write it like only g, and this one we have the del by del x, del by del y, del z, we can use it nebula, and in this case we have a stress. Okay, is a multiplication, so we can call this tensor stress I and j. So it should be xx, it could be xy, it could be yz, anything. Okay, so we have the simplified form in this case. So rho, this is f is equal to ma, so we have the rho, and in this case this will be cancelled out, right? This part, and this part. So we can simplify it like this. Okay, so finally we have this equation. Okay, so the same thing we can consider for x directional, y directional, and z direction. So just simplify it like this. This one is u, v, and w. We have gx, gy, gz. Okay, and we have sigma x, and we have yx, zx. Remember that if you are writing x, along the x, so x should be later, okay, and the contribution y towards x, contribution of z towards x. It's so similar way, contribution of y towards y, this is the actually normal, this one is the share, so we have the contribution of x towards y, contribution of z towards y. A similar way, the contribution of z towards x, contribution of x towards z, contribution of y towards z, and contribution of z towards z. Z towards z should be also normal. So we have these three equations, okay. So now we move a little bit forward. So we just consider the concept of fluid is at rest or fluid is moving. When the fluid is at rest, okay, only the stress acting at any surface of any fluid is the local hydrostatic pressure, which always acts inward and normal to the surface. When the fluid is rest, we only consider the normal component, okay, we only consider the normal component of the fluid. We don't have any shear at that time because the fluid is not moving, the fluid velocity is 0. So in this case we have, you can see is all are actually same, p. So it means that we don't need to consider the orientation at that time. When we have the fluid at rest, okay, the stress vector is actually, even though we have the stress vector, you can write x, y, xz. So this one is x component, this one is y component. So we have yx, yy, yz. We have this one is z component, zx, zy, zz. So we only have these normal velocities, okay. Other terms, the orientated term or the cross coupling, all are 0. Because the fluid is at rest, we don't have any shear. And in this case, the direction is minus, because it's always act opposite. It's pressure, right? It's always act perpendicular to the surface and inward direction. You can see it always act inward and normal to the surface. So that's why we have the minus sign. So this is in the case of fluid at rest. And then when we have the fluid moving, so then we have the stress and we have the shear stress, okay. So we will have two components. So this one, we will have two things. One is the normal component, another one is the shear force. In case of shear, we use a tau. So tau xx, xy, yz, tau yx, yy, yz, tau zx, zy, zz. Okay, so we have the x component, y component, and z component. So this is the normal part, and this one is the stress, the shear stress part. So we call this tensor is called this, in this case these are all viscous stress, or we call this shear stress tensor, okay. Okay, so as we have this one, so we have to know about something related to the Newtonian fluid. So what is the Newtonian fluid? Newtonian fluid, as I said last time, you remember that where the stress tensor if you remember, I mentioned that where the shear stress is actually proportional to the strain, okay, du by dy. A similar thing it will say here, Newtonian fluid is defined as the fluid for which the shear stress is linearly proportional to the shear strain rate, or rate of change of shear strain is proportional. So Newtonian fluid actually is analogous, as I said, like in case of solid mechanics we have the stress strain relationship. You know that in case of solid mechanics we have a stress by strain is Young modulus of elasticity. So we have this one, the Newtonian fluid is also maintaining the same Hooke's law, okay, where the stress is actually proportional to the shear strain rate, and it will maintain until the yield point. It means the proportional part, okay. So it's always proportional. If it is not proportional, then it's not Newtonian fluid. Many common fluid, for an example, the air, gas, and other gases, water, kerosene, all the oil-based liquid are actually Newtonian fluid. And on the other hand, what is non-Newtonian fluid? It's the same. It means that when it's not linearly related, it means it's not related with the shear strain. It can change abruptly. Okay, for an example, it means the cake, batter, paste is blood. Okay, so in this case, the stress and strain are not proportional. Okay, so it's not following the linear ways. It's different. So we call this Newtonian fluid exhibit a memory. It means the stress, when you release the stress, it is not gaining its actual position again. You have to remember, it's like plastic, okay? So it means that you apply the pressure and then you release, it's not actually gaining its actual what can I say, actual conditions. Okay, so the shear stress depends not only on the local strains but also its history. So it has some memory. So if you have the pressure, if you see the paste, okay, if you keep the pressure and you release the pressure, you will see your trace, the trace of your maybe if you hammer it, you will see the trace of the hammer on that. If you put your fingerprints there, you will see the trace of the fingerprint. It takes some time, and sometimes it's not regaining its actual position. Okay, it's like paste. You apply the pressure, it changes formation, but when you release the pressure, it's not gaining its actual condition. So it will have a trace. Okay, it will have its memory. So that's why we call this non-Newtonian fluid. So if you just plot it, the strain and strain rate, stress and strain rate. So this one is linear. This is a Newtonian fluid. This one is a shear thinning, and this one is shear thickening. So in this case, we have these two differentiated, two different non-Newtonian fluid. We have the shear thinning and shear thickening. Okay, so you can see this shear thickening means it takes more values here. You can see for this strain, this much strain, your stress is here. On the other hand, if you focus here, for this much strain, you need more stress. So we have the shear thinning and shear thickening. Thicken means like it's thickened, so it's getting down. Okay, and thinning means it's lighter. So that's why we define it as lighter and thicker. We use the term here. Okay, so this is just for your knowledge. So next is we will continue the derivation so in my next video. Okay, thank you very much.